Hi, everybody. My name is Dave McMahon. I'm from UC Berkeley. I'm currently working as the chief engineer for the Breakthrough Listen project, which I'll talk a little bit about on this talk. We operate out of this thing called the Berkeley Steady Research Center at UC Berkeley. I'm officially in the organizational research unit called the Radio Astronomy Lab at UC Berkeley, if you know anything about that. So I'm going to talk about how I use Julia in radio astronomy / interferometry. And the spoiler alert is I use it to find aliens, which I haven't found yet, but that's what we're doing. So I'm going to give a little bit of history of radio astronomy. I'm not sure what the people's background is here, but I figured it would be kind of maybe broader people who aren't so working day in, day out of radio astronomy, where it came from, and the history. Actually, I learned a lot preparing for this part of the talk. It's my favorite part of the talk because it's kind of interesting. I'll introduce Breakthrough Listen. Like I mentioned, that's the project I'm currently working on. I got a few slides, a little bit of a menagerie of some radio telescopes and things, just a little eye candy stuff. And then I'll talk about Julia and how I use Julia. So the history, it's actually prehistory of radio telescopes, radio astronomy, because, I said in the abstract, optical astronomy has kind of been around since people could look up at the night sky. And you guess you could argue maybe it didn't really start until Galileo made his telescope and looked at the moon and Jupiter and drew the moons of Jupiter and got in a lot of trouble with the church because of that. So that still was like the 1400s, I think. So Maxwell's equations, like the mid 1860s, 1870s, something like that, predicted electromagnetic radiation, which is what we call, if the right wavelength, we call them radio waves. And so it didn't take scientists, physicists too long to hypothesize that maybe you could detect radio waves from space. And so people started to do that. But they kind of failed because of various different reasons. A lot of them was they didn't really know about the ionosphere until 1902, and they were observing at some low frequencies then. And as you may know from ham radio skipping or whatever, low frequency radio waves do not pass through the ionosphere. They bounce either back at us or they bounce back into space. And so those were not so great. There was one guy who stretched out a very long wire on top of the mountain in the Alps, and he was trying to detect bursts of radio frequency energy from the sun. He might have been successfully at the sensitivity and the frequency was okay. So it might have been okay, except these bursts happen during solar maximum most often, and he was observing during solar minimum. So he kind of bad luck on that one. There's one other sort of non-starter for the radio astronomy, I guess. These guys, this is 1924, Mars and Earth were passing very close to each other. And so they called up their politician, I guess, or I don't know who they called up, but they got in touch with the Navy or the Pentagon or whatever, whoever sent this telegram, and they requested the Pentagon, they convinced the Pentagon that they wanted to listen for Martians that might be transmitting to us during this close passage. And so they had the Navy turn off all the radio transmitters during the time of closest passage so that they could listen for Martians. But apparently the Martians were doing the same thing too, because they didn't hear them. So they also failed, unfortunately. It wasn't really until 1932 when Karl Jansky detected radio emission from space. But of course he did it by accident, because if he tried, he would have failed. So he did it by accident. He was actually working for AT&T Bell Labs in New Jersey, I believe, at the time. And they were building a transatlantic radio telephone. And they had some sort of hiss in their signal, and they wanted to figure out what that was. And so we built this antenna that kind of spins around little wheels. I don't know if you can see the wheels on a little round turntable. They have a reconstruction of this antenna at the Green Bank Radio Observatory in Green Bank, West Virginia. He found two sources were related to storms. The third source he found was something that just sort of happened, and it happened every day. And he thought, well, that's kind of weird. And then he noticed that it wasn't like every 24 hours, it was every 23 hours, 56 minutes, which implies that it's something on the star, well, like in the cosmos, in the sidereal day, they call it. It's fixed against the stars. It's not, it's part of the sun-Earth cycle. So it turns out it was the, probably maybe Sag Star, actually. It was a galactic center. So before you imaged it, he detected it, I guess. So 1932, that was the first thing from space, radio emission from space that we detected. I was talking to someone at one of the evening events this week, and my understanding was, or maybe it was Monday, anyways, my understanding was that he was transferred to a different project and didn't really pursue this. But I'm not sure what the full story is, but he didn't really take it anywhere. And this guy who was, I guess, a college student around that time, graduated. His name was Grote Reber. He actually built the first parabolic dish reflector to capture radio waves from space. And he was the first and only radio astronomer in the world for about 10 years. And even with this telescope and everything, it took him a couple of years to get it to work and actually get data in. But he did succeed. He was quite successful. He wanted to publish his results, and he had some challenges finding a peer-reviewed journal that would actually take it, because the astronomers didn't understand the radio part of it, and the radio engineers didn't understand the astronomy part. And so went back and forth with the editor, and eventually they published his paper unreviewed, which is kind of amazing. But it was legit work, and people did quickly, follow up with other work in a similar vein. After World War II ended, all these radar engineers sort of had, to find new jobs, I guess, and some of them went to radio astronomy. So that was pretty good. And from there, the field took off to where it is today. In 1960, Frank Drake started Project Ozma. This is sort of perhaps one of the first radio SETI experiments. Frank Drake, maybe you know of the Drake equation. It's sort of a formula that's just designed to sort of estimate how many civilizations there may be, communicating civilizations there may be in our galaxy. And it has a bunch of terms in it. I won't go through that today, but it's a fun thing to talk about. This is sort of his setup here in the upper left corner there. It's kind of fun to go to see these old things, and they have the big knobs and the fancy lamps and the switches and everything. But this was their back-end system they had back then. It's a chart recorder. It's not a lot of resolution. This was, I guess it was observing on Christmas Day. This is 25 December. This is a modern back-end. Looks kind of like a cluster. This is the Breakthrough-Wilson cluster. We have at Green Bank now. It's about 72 compute nodes, a few more actually since these pictures were taken. Mostly a lot of disks and GPUs and network cards, which I guess is what computers are these days, or clusters. This was the early archive, how we archived his data. With chart recorders, you just put them in a cardboard box and you put them in a cabinet, and then there it is. It's not really indexed or anything like that. Good luck finding something. This is what a modern archive looks like. It's like the same thing. So Breakthrough Listen is the project I am currently engaged with. It was announced back July 20th, 2016 at the Royal Society in London. And it's from the Breakthrough Initiatives. It's the first of the Breakthrough Initiatives. The Breakthrough Prize Foundation started these initiatives. They do the Breakthrough Prize Awards every year. In fact, your group got a Breakthrough Prize Award. There's a funny story I can tell you after hours about that whole situation. It's a 10-year project, $100 million. It's a pretty good chunk of change. These are the people that were there at the announcement. Yuri Milner's the prime sponsor, Stephen Hawking, Lord Martin Rees, Frank Drake, and Anne Druyan, Carl Sagan's widow. And they had some big statement and signatory, a lot of pomp and circumstance with the announcement. So that's sort of what I do. It's initially we started with 3 different telescope facilities. The Automated Planet Finder, it's an optical component, so I don't do much with that. But that's in California, very near to Berkeley. It's just down in San Jose, up on Mount Hamilton, Lick Observatory is there. The Green Bank Telescope in Green Bank, West Virginia, that's part of the eye candy coming up, just so you know. It's very large, and it's quite an amazing facility that this thing is so huge and they can still point it so precisely on the sky. It just blows my mind every time I think about that. And we were also on the Parkes Radio Telescope. It's now called the Murray-Yang Telescope at the Parkes Observatory. It's in New South Wales, Australia. This was famous for, the movie called The Dish, but also it was one of the downlinks for the Apollo moon mission. So I'm not sure if it was the actual stepping onto the moon that was video, but it was a lot of the video of that whole thing. It's if you've seen the movie The Dish, it's actually a really good movie. If you haven't seen it, I would suggest you see it. It's quite a charming little film. Now these are all the facilities we're at now. We have about, I guess this says 16, or it said 16 before I expanded the list. We're basically almost on every continent. I think we don't have anything on Antarctica yet, but we sort of have a global domination. I guess we're kind of in competition with you, but we get lower frequency, so it's easier for us to engage with people. And we also operate a lot of times in a commensal setting where we will just take a copy of the data that some other observer is observing some other source, because we don't really know where ET might live. So anywhere place it's good to look as another place. We tend to look at stars when we do our thing because stars have planets, and presumably people live on planets. There could be a Battlestar Galactica kind of concept, but so here's the menagerie part of the talk. This is the Green Bank Telescope. It's kind of like the Golden Gate Bridge or any big bridge. They have to paint it regularly, and so these are the painters here lined up with their hard hats on over there, and they have this sort of forklift kind of thing here. And this is the Green Bank Telescope, and those are where the people are down there. And you can see the pickup truck sort of for scale. I mean, it's 100 meters, diameter. The aperture is 100 meters. I think the surface is probably about 110 because it's kind of at an angle. It's just a really, really cool place to visit. This is not a radio telescope. This is the Leviathan telescope. This is an old optical telescope. It's in Ireland. It's at the Burr. It's in Burr at the Burr Castle. There's a LOFAR station there, and we do actually work. We have some back-end equipment at that LOFAR station and at the Sweden LOFAR station for low-frequency observations, and we do some simultaneous observations, which is kind of a fun way to cut down on RFI false positives. But this telescope is very famous because the guy who built this was the Earl or something of this county or whatever region it was, and he would go up every night and look at this thing, and he would have a drawing of this M51 Messier, catalog, and this is the 51st object, and he would just keep updating his drawing, talk about your averaging of your images, and in a form of integration, a sort of artistic integration, he would just every day kind of tweak his drawing to see whatever parts he could see the best, and he was the first person to resolve the structure of galaxies. Before they were just fuzzy blobs, and he tried to get some of his colleagues or other astronomers in the UK interested in this, and they're like, no, it's some instrumental flaw. Don't bother us with this silliness. And eventually he convinced them to come out and look for themselves, and they did, and they're like, oh, wow, it is real, okay. So it's now known as the Whirlpool Galaxy, which they didn't call it that until they resolved the structure and everything. So, it's a fun story and more history. But that, again, that was, I think, in the mid-1850s. I think that predated even Maxwell's equations, possibly. It's right around the same time. We also work on telescope arrays. So on the left is the Meerkat radio telescope array. That's in South Africa. It's a very powerful telescope. They've made some fantastic maps of the galactic center, much larger scale than yours. But they've made some really cool maps with some really bizarre filaments and such. How are we doing at time, Paul?
You got 4 minutes.
4 minutes, sorry. The bottom one is a very large array in New Mexico. We have a big back end on that, which I was going to put out, but I just had to stop at some point with the eye candy. Let's get on to the Julia stuff. This is also Allen Telescope Array at the top. We take a lot of students up there and everything like that. It's kind of a teaching array, and it's operated by the SETI Institute, actually. But we work with them up there at that facility. That's in Northern California. Okay, Julia. How to find ET. This is a test signal sort of that we use. It's not really a test signal, it's just a signal from the Voyager 1 space probe. And we use it as sort of what a putative ET signal might look like. It's drifting in frequency. So the horizontal axis is frequency, the vertical axis is time. We call this a waterfall plot. It's shifting in frequency. This is very finely channelized. This is the carrier from the Voyager 1 signal. There's some sidebands that are a couple, 22 kilohertz out either direction. And this is drifting because the Earth is spinning. It's primarily due to Earth's rotation. And so as the Earth spins, it's an acceleration. So, the Doppler shift is because there's motion between the transmitter receiver. It's like an audio thing with the train. Gets quiet, higher and higher in frequency, and then whistle goes down. So the shift is because of the velocity, but the drift or the change in the shift is because of the acceleration. Rotation is an acceleration kind of thing. And so what we want to do is we want to find this signal and we want to add it all up. And so what you want to do is you want to kind of stack them. You want to kind of undrift the signal. And you can do it two ways. You can do it through just doing a discrete shift by integer number of channels, just sort of sliding them over. You don't have to actually slide them, you just like move, index differently, but it sort of effectively does this sort of thing. Or you can also do a Fourier domain shift where you take the FFT of the spectrum, multiply by a complex sinusoid, inverse FFT it back, and then the signal's been shifted. There's a little bit of wraparound at the ends, but we usually do really wide bandwidths and not that much shifting. So we just ignore the little edge effects. And then you can integrate down over time. And so when they're all lined up, you get this sort of big spike. And when they're not lined up, you get the red curve. It's just sort of not so bright. And this is a pretty bright signal, actually, with the Green Bank telescope, and it's been super channelized. So, it's right. This is, for us, that's the high SNR kind of signal, even though it's actually quite low. But radio astronomy is just all about low SNR. It's like mostly just noise. So we need to integrate to get the noise down and the power up. So you can do this one by one. If you do this, this is one drift rate we chose. It happened to be 2.37, which was the magic one to do. If you do it at different drift rates, and this becomes like, if you could imagine this, instead of being a curve, you could imagine a color, like a row, raster row, and a heat map. And so if you do that for all these different drift rates and different starting frequencies, you get this thing, which we kind of call a butterfly plot or something. It's a frequency drift rate plot. And you can see all the power is at this drift rate, and the drift rate and the bright spots. It tells you the start channel and the drift rate. And it turns out that you can use the Chirp Z transform to kind of do this like all at once for a whole bunch of drift rates. So you FFT the spectrum, you do a Chirp Z transform. This is sort of you start up on the upper left. You do that's your time frequency sort of waterfall plot spectrogram. You do an FFT of that into the Fourier domain, and then you do a Chirp Z transform, and then you do another inverse FFT back, and then you end up with your FDR plot, and it's pretty cool and fast and interesting. I wrote an implementation in Julia. It was super easy to, I just wrote it using arrays and FFTW, but then it was super easy to switch to cuArrays and CUDA FFT, and I profiled it and was able to get it all, parallelized, so everything happens in parallel. And the limitation factor here, it's I/O bound, it's actually O bound. This is the memcopy device to host of the output data, and it's just sending data out as fast as it can. And so it's not compute bound, and so we can do more of the compute on the GPU perhaps. So there's some room for moving the compute. Also visualizing data. So one other thing I use Julia for, this is some Green Bank data. This Iridium satellite stuff is really a problem for us. They've had more launches since our program launched. They've had more and more space vehicles going around, and so I think it's become more of an issue for us. You can see it really corrupts our data because it causes overflows in the FFT for that sort of portion there. And so then if you look at the bottom left plot, that's a big long, it's only an hour, I guess, and each little gray line is a scan that we do, but you can see the total power. The satellite kind of comes and goes. It's not so good. And so then I use Satellite Toolbox and get all the 2-line elements for the Iridium satellites. You can make a little sky map of where the satellites were for the 5 minutes of this scan. And it's sort of like, the little circle, black circle is where the telescope was pointing. The traces show where the satellites were going. And one of them came pretty close. So that's another thing. And it's just super convenient to do all this stuff This was like all those. You see the packages that I used there. Voyager localization. We're also trying to do some beamforming on the Voyager test signal. We can't get the location from JPL Horizons. They tell us where they think it is. It's pretty close. Like, it's close enough for the GBT to see it and find it. But when you're doing the VLA beamforming on it, it's the beam is much, much smaller, the synthesized beam size. And so you beamform where JPL says it is, and it's not there. And so we wanted to find out where it actually was. So we did some sort of little raster scans sideways and vertically, like in right ascension and declination on Voyager's location. And then you take the total power and you can do like fit a Gaussian to the beam shape and that sort of thing and find out where it is. And this is talking about some of the hash pipe data buffer stuff that I was, Kieran talked about. And these are the repos that I have for some of the stuff I've written. You can look me up. I have my own little registry there if you want to just add that and use my stuff. That's an easy way to do it because I haven't really registered any of these in the general registry yet. So that's it. Thank you.